Today we are very happy to have our own Dave Anderson. It's still going to be a two-part series. The first part now, the second part tomorrow morning. And today we'll have introduction to equivariant K-theory. Tomorrow we'll have more serious introduction to equivariant K-theory, I suppose. And there's Dave Anderson.
So thanks for giving me this opportunity to speak and this opportunity to kind of go into the just background of equivariant K-theory. And also I beg your patience with my voice. You can hear me about 10 times better than you could have if I tried to talk to you yesterday. So I'll try to project as much as I can, getting over it. Today, I started planning lectures on equivariant K-theory, but I figured it might be useful to just do some regular K-theory. So June has very accurately described today's talk as an introduction to the introduction. Let me give you what I think of as a very quick background. So some people have been going around as long as I've been here asking what's the point of K-theory, and I'm gonna give you one take on that. So one thing that you might want to know about is something about global sections of vector bundles, say, for a vector bundle of a variety. So that's, I'm going to take it as given. That's a pretty long problem with a pretty long history. And well, Grothendieck realized that a way of framing the Riemann-Roch problem is that this, and I guess people before this had realized this too, Hirzebruch and even as far back as Riemann and Roch, it's better to look at the Euler characteristic. So something like the alternating sum of cohomology groups. This has better formal properties. It's going to be easier to compute. And in particular, this is now particularly Grothendieck, around 1957, in Princeton, I don't know whether it was here or up the hill, he introduced in lectures the group K0 of X. I don't think the zero is there yet. As the a universal source for functions, for additive functions, and I'll explain what that means. Like the Euler characteristic. Okay, so that's where K-theory might come from. Equivariant K-theory, I'll say a word about it. So it was born not too much longer, not too long after just the ordinary K-theory. So why might you want to look at equivariant K-theory? Well, two reasons come to mind. One is that you can use a G action to simplify calculations, and that's one thing we'll do. So particular localization. And secondly, you get some info about G representations. And as an example of that, let me just mention that if you do non-equivariant K-theory of P2, you can see, for example, that the dimension of the space of global sections of O of 1 is 3. Okay? You can see that other ways too. But the information of keeping maybe a torus around will give you information of the character of this group. And maybe it's like something like 1 plus x1 plus x2. So we'll record the characters doing as lattice points in some lattice. So this is kind of finer information than you would get from just the non-equivariant string. Okay, I'm not going to write down a whole lot of names, but the algebraic version of equivariant K-theory was sort of developed by Thomason in the 80s and further developed by Mercuriev, Vetsezi, Vistoli, and Edit and Graham in the 90s and 2000s. And there is a whole story of higher algebraic K-theory, and I'm not going to go into that at all here. So only Grothendieck groups with maybe one or two little digressions. Okay, so that's all I'm going to talk about here. Okay, so let's get to definitions. So yeah, definitions. And conventions. So X is going to be an algebraic variety. And it's going to be quasi-projective to keep some technical things under control. And it's going to have a linear algebraic group acting on X. And almost always G is going to be a torus. I'll say a couple things about the general definition, but quickly I'll specialize in the torus case. And when I say X is quasi-projective with a G action, I want that G action to extend linearly to the embedding in projective space. Okay, so we've got two kinds of K-theory, and they're subtly distinct, but it's important to keep them separate. I'll say some more things about that. So you can look at K-theory of equivariant vector bundles, and this gets written like this. And all it is the free abelian group, or the abelian group with generators given by isomorphism classes of equivariant vector bundles. Modulo this kind of ubiquitous relation, which enforces additivity along short exact sequences. So I presume like pretty much everyone has seen this kind of thing before, but it bears repeating. Okay, so that's K-theory of equivariant vector bundles. And this category of equivariant vector bundles sits nicely, well, it sits inside the category of equivariant coherent sheaves. And I'll write that with the indices swapped. What you should be thinking of is this is like the 0th part of a homology theory, and this is like the 0th part of a cohomology theory. And that's what I'm doing. That's what I'm saying. So this is really the same thing. So isomorphism class of an equivariant coherent sheaf modulo exactly the same type of relation. And I guess maybe should I say what an equivariant vector bundle is? Yeah, maybe I should say. So an equivariant vector bundle is just, well, it's a vector bundle where the G action is, the projection map is equivariant for the G action. So I do the projection map of G times something in E. That's the same thing as G times that. G times projection of E. And we need some linearity. So if I look at a fiber over a point in X, this equivariant says that there's a map that I multiply by G it sends me to the fiber over d times x, and that map should be linear. So that's what an equivariant vector is. An equivariant coherent sheaf is a little harder to write in this way, but you can translate this into some diagrams and axiomatize it that way, and that's what okay. Okay, so let's look at the relationship between these groups. So every equivariant vector bundle is a coherent sheaf. So we get, and an exact sequence of vector bundles is an exact sequence of coherent sheaves. So we get a homomorphism, canonical homomorphism from K theory of vector bundles to K theory coherent sheaves. Just take vector bundle regarded as a coherent sheaf. So this is neither injective nor surjective in general. But importantly, an isomorphism when X is not linear. And I'll say a little bit more about that isomorphism shortly.
That's good, you mean regular.
Yes, I mean regular. Don't mean smooth. Okay, so let's see. In either group, we have addition. I mean, addition is sort of formally defined, but one way you can realize it is by taking direct sum, either of vector bundles or coherent sheaves. But in K-theory vector bundles, you also have multiplication. Tensor product. Because you can tensor two vector bundles and get a vector. Yeah.
Sorry, can I also tensor two coherent sheaves? What goes wrong there?
So what goes wrong there is that tensor product by a locally free thing preserves exact sequences. Tensor product by a general coherent sheaf does not. But in fact, tensor product of a vector bundle by a coherent sheaf does preserve exact sequences. So let me finish my sentence. This is a ring, tensor product, and K3 of coherent sheaves is a mod over K3 of vectors. So that's always the thing. When you think of an operation that you could do on a sheaf or a vector bundle, you have to keep track of what it does to exact sequences, and that'll come up. That comes up in K3. Okay. So vector bundle times a coherent sheaf is just vector bundle tensor coherent sheaf. Okay, so this is further analogy of, now I'll go ahead and write it down. This is like cohomology. So this is a slogan. And K theory of coherent sheaves is like homology. So that's the slogan. Should keep in mind. And this kind of map is a cat product. So let me just write down a couple first examples. So the ordinary K theory of a point, well, it doesn't matter whether I look at coherent sheaves, vector bundles, that's just Z because vector spaces. are determined by dimension. On the other hand, if I look at the G equivariant K theory of a point, again, it doesn't matter whether that's vector bundles or coherent G's, they're the same. That's what's called the representation ring of G. Okay, so it's generated by isomorphism classes of representations, and the operations are tensor representation of representations. So virtual representations in general. So let's look at another important example, the second one. So let's take G to be just the multiplicative group. And then its character group, which I generally write as M. So that's just by definition, homomorphisms of G into C star. So this is isomorphic to Z again. And the isomorphism identifies an integer with the homomorphism that spends Z and C star to Z. Okay. Well, this means that the representation ring, so every algebraic representation is just given by a character. So R of G in this case is R of C star. It's naturally the group algebra of the character group, which is Z. So I can write it as Laurent polynomial. Or I'm using X to denote the standard character, the identity. So hopefully this is okay. And then continuing this, if I take G to be the torus, then the representation ring of the torus. Oh, let's say. The character group is isomorphic to n copies of Z by same isomorphism. And so the representation ring is naturally the group algebra of the character group. And choosing a basis, it's a Laurent polynomial ring in variables. Okay. So at this point, I should say, I said in the abstract that these are sort of complementary lectures to Bill's lectures on equivariant cohomology. And here we see something pretty similar to the equivariant cohomology of a point, which was a polynomial ring in n variables. Now it's a Laurent polynomial. So later, and pretty much from now on, I'll use e to the t1 and e to the tn. I'll use something like this, e to the ti. I'm gonna want to use xi for other variables. So I'm replacing things that look like e to the ti. That's a common thing to use when writing representations. Okay. And I guess I should say at this point, from now on, G is a torus. Many of the things I'll talk about work for more general G, but some of them don't. E is the place I want to work with. Okay, so let's get down to, so the next 20-30 minutes, I want to talk about some basic properties of these, and then give a couple of examples. So here are some of the basic properties. Functoriality. So P theory of vector bundles is contravariant. There's not too much that needs to be said about that. You can pull back vector bundles. P theory of coherent sheaves is covariant. You can push forward a coherent sheaf, but you might not get a coherent sheaf. If you push forward, you need it to be, you need your map to be Okay, so it's covariant for proper maps. And let me write that down. So here again, you have to worry about what happens to exact sequences. So if I've got a map, and equivariant, so equivariant kind of goes without saying. This point, everything has to be equivariant. Then I get push forward, proper push forward. I'm going to define it on coherent sheaves. So I want to define the push forward of the coherent sheaf, and I would like to say it's just, I'll take the class of the push forward, but of course you have to correct by the fact that this might not be an exact functor. So you start subtracting higher values. And that whole thing will respect exact sequences. And I'll say two more bits of functoriality. So in theory of coherent sheaves is also has flat pullbacks. So if you've got a flat morphism, then you get a pullback map on K3. And that just sends to this pullback. And that's because when F is flat, the pullback now this is exact. Okay, so far, this should, so K theory of coherent sheaves should remind you of Chow groups or Borel-Moore homology, which has these properties. Okay, and the last thing I'll say is that, so this, I guess this works for any map of Torah, but let me do it for an inclusion of I. So we have if you've got a subgroup, you can restrict a representation, and that gives you restriction maps on both. And they both go by restricting to the smaller torus. So in particular, you can take the smaller torus to be trivial and get ordinary K3 back from Equivariant. And let me point this out because this is sometimes the cause of confusion. So this one is surjective as a result of mercurial UNL. And this one is not necessarily surjective. So there's another difference between Equivariant K3, between K3 dash bundles and coherent sheaves.
Does the map T to T prime need to be injective to have a mapping?
To have a map, no, but for this statement, yes. Yeah, so there is a map always in either case. Okay. And properties, and we'll see. So, yeah, so my goal in kind of giving you these properties is just to show you sort of what's, so my idea is that everything here should be mostly easy. At least pretty close to the definitions. So there's a particular exact sequence which sometimes gets called localization, but it is not equivariant localization. So if we have closed subvariety and its open complement, then we have an exact sequence. On K-groups. Okay, so this works for coherent sheaves. And, so this is a push forward. If you push forward along a closed embedding, you get a coherent sheaf. And this is pullback. So if you pull, this is the flat pullback I mentioned originally. So the embedding you use flat. Okay, and surjectivity of this is not so hard. It says that you can extend any coherent sheaf equivariantly along an open embedding. Yep. So this statement is not too hard. So this is exact. If or to at least indicate a special statement about equivariant or about course equivariant K theory, which is that structure sheaves of subvarieties generate the K theory. So as a module over equivariant K theory of a point by structure sheaves OV, where you're looking at closed invariant subvarieties, and I guess irreducible. So this is another way in which K theory of coherent sheaves is formulating child groups. So the proof is basically use the exact sequence to reduce the affine case, I guess, and the theory and induction. And then you can use the Visage. Kind of Visage argument, which is just say that any equivariant sheaf on an affine scheme breaks up things that look like this. So that's and the key here is that there is a non-empty, there is at least one non-empty open T invariant subvariety, which might not be true if T is not a torus. So the statement is very specific to torus. Okay. So let me do, okay. Examples. If I take affine space and I project it to a point, then I get K theory of a point. And that's the representation ring. I wrote it down over there. And pull it back to the K theory of affine space. And this turns out to be an isomorphism. And so you can show that using this. There's other ways to show it too. But in particular, this shows that K theory of affine space is a representation ring. So another one for our polynomial. And essentially what's going on here is this is an incarnation of a multigraded Hilbert syzygy again. It's saying you can find a finite free resolution, multigraded graded with respect to the character group of T of any module in affine space. What other properties do we have? We'll get through a couple more properties and then states, and then we'll look at projective space. So there's a more general statement, which is that so this mobilizes to a general statement, which is that if you have an equivariant vector bundle, so in particular, this is flat, and then the flat pullback map is an isomorphism. So this is the kind of thing that you might hope for from a cohomology type theory or homology theory, and it's true. Is that right? Okay. And then let me write down the Poincare isomorphism that I alluded to earlier. Okay, so X is non-singular or regular. And then this map, which takes a vector bundle and interprets it as a coherent sheaf, is an isomorphism. And the main point here, it's not the end of the proof. The main point is that in this context, every equivariant coherent sheaf on X admits a finite resolution by equivariant vector bundles. Okay, so this is basically the multigraded Hilbert syzygy again. And because of I'll just write out what I'm talking about. So if I've got a coherent sheaf, then I can find some vector bundles on X that resolve it, and this sequence terminates. And then I can say that the class of F can write it as an alternating sum of the classes of E. This is a finite sum, so it makes sense. So I know this is a little dry, and I promise tomorrow is going to get a little bit more. We're going to have some applications tomorrow, but I can have. All right, so in a moment I'll do projective space. Yeah.
Oh, sorry. So I guess in the usual proof of Hilbert syzygy theorem, you also like bound the length of a free resolution. Can you get a bound on the length from this style board from like the K theory or no?
Maybe I was unclear. So this is the direction of implication goes the other way. So this implies that.
Okay.
Yeah, you don't get anything particularly new. It's not that I know. Yeah, so let me give one example. So X is not singular, and V and W are invariant subvarieties. Then it basically follows from translating the structure sheet of V and W into an alternating sum of vector bundles, that product of structure sheaves is given by Tor product. And so that's how you do products of structure sheaves of subvarieties in K-theory. And an important property of the Tor product is that each one of these sheaves is supported on the intersection, because it comes from tensor product of these two. So each one of these is supported on the intersection. So if the intersection is empty, then the product of sheaves is 0. Okay, so that's another thing you might hope. So it's true. All right, so I'll leave that there and then continue. Right, so for the last 5 to 10 minutes, I'll talk about projective space. And then if there's time, which there may not be, I'll talk about rest modules. Okay, so this is the kind of setup that we're gonna look at today and then a lot tomorrow too. So I've got a torus acting on a vector space by characters. It's U1 and UN. So all that means is that in a basis, I've got an element of the torus. I've got a vector. This is just e to the U1 evaluated at z A1 e to the UN. That's how they're scaling. Is this okay for everybody? So I'm just telling you some numbers to scale each vector by, and these are functions on the torus. Okay, so then you get an action of T on the projective space, and it fixes in particular the coordinate lines. So here PI is the it's just the ith coordinate line. Okay. So that's the setting we'll be looking at. Oh yeah. If the characters are distinct, these are exactly the fixed points, if and only if. These are all the fixed points. This is Pn minus 1, I guess. Okay. So let's try to work out the K-theory of this. Okay, so we have hyperplanes. Oh yes, I should say the coordinates. Yeah. The P n minus 1 has coordinates. Next one, xn. And these are kind of dual, so the characters, the corresponding characters are minus U1 up to minus UA. But you think of these as dual vectors, right? So vectors. So then we have hyperplanes. E5. And that's just where the ith coordinate vanishes. And so I can write down an exact sequence. So you're used to looking at the ideal of a Shiva hypersphere plane is O of -1. This map is multiplication by xi. And so that means I should be tensoring with a character to put this in the right degree where the xi moves. Okay, and this tells me that OHI is equal to structure sheaf of the ambient projective space, which is usually called 1 minus e to the minus ui times. So let's do the simplest possible, not completely trivial example. So on P1, we've got a point that we call 0. And I guess my conventions are such that this is the second type of plane, infinity. Which I guess is the first thing, sorry. Okay, so this calculation says that the structure sheaf of 0 is 1 minus e to the minus u2. I'm sorry. Yeah, minus u2 rho minus 1. And O infinity is 1 minus e to the minus u1 rho minus 1. But I can rewrite that as e to the e to the chi, and I'll tell you what chi is in a second, times 0 plus 1 minus e to the chi 1. Where chi is 2 minus e. So all I've done is just kind of moved. And in particular, if I've assumed that the characters are distinct, the only T invariant subvarieties are these and all of P and P1 itself. So by this generation theorem, I know that these structure sheaves together with O of P1 generate the K theory. Well, there's a relation between these two that I wrote this one in terms of, I wrote the second in terms of the first. And so I get to conclude that the K theory of P1, and it's non-singular, so this is the same thing as coherent sheaves and vector bundles are the same. It has an RT basis given by 1, which is the structure sheaf of P1, and 0.
So when you write O minus 1, the linearization is coming from the.
It's coming from the natural action on V. Yes. So when I write, when I write O minus 1, this is, it's important to keep track of this as a T equivariant sheaf, and it's in the natural way. So it comes from the natural sequence. So it's important not to just write O1 here, by the way.
That's C2 in the middle. Should that be a V?
Sure, it works. So I did it for P1, but you're right. So this works for me. Okay, so it looks like I better wrap up. So let me write down a presentation for this ray. And then I'll have left myself quite a big job for tomorrow, but I'll try to make the best of it. Okay, so let's write So it turns out that this is a good class to look at. So rather than just the class of O of -1 or maybe O1, 1 minus O of -1 is a good class to look at. And I get a presentation. So K theory of E1 is the representation ring that join one variable, which I'm going to call zeta, modulo the relation zeta minus 1 minus e to the E1 times 1 minus e to the U2. Oh, sorry, times zeta is 1 minus e. Okay, and the reason I know that this relation holds is because if I translate it back into this, I see that this is equal to e to the U1 times O of infinity. And this one is e to the U2 times O of 0. Well, these characters are just like scalars and they come out. So I multiply O of 0 times O infinity, and I get 0. I have this property. Okay, there's a similar presentation for any projective space. And I'll leave it to you to write it down. And so tomorrow I will talk about the localization theorem, some applications of the localization theorem, and Riemann-Roch.
Any quick questions?
Here you have an equivariant. What does that mean? Like it's rejectional chloride?
So I'm gonna make a statement. For a surjection of current, so you always have these maps. You always have these maps. And the only place where I know I can say anything definitive about these maps is in the inclusion case. And in that case, it's surjective. And again, only on the vector bundle side, so only on the coherent sheaf side, not on the vector bundles. So yeah, you have the map, but I don't know anything in general.
Okay, the lecture will be continued tomorrow and get the room ready for the next.